Hi everybody, my name is Vicky Prakash and today I'm here to talk about a presentation by Vasily Volko about better performance at lower occupancy. Now there is a popular misconception that if you want to hide latency, multi-threading is the only way. That is, you need to run more number of threads per multiprocessor or run more number of threads per block. However, the result of multiplication of two large matrices on GTX 480 GPU has shown a deviation from this popular misconception. Where on QBLAS 1.1 we were running 512 threads per block with an occupancy of 67% to get the performance of 128 GFLOPS per second. On QBLAS 2.0, by using 8 times lesser number of threads per block and with 2 times lesser occupancy, we have achieved a performance which is 1.6 times better than the earlier one. So in this conversation, we are here to talk about how to hide arithmetic latency using fewer threads, how to hide memory latency using fewer threads, how to run faster by using fewer threads, and a case study on matrix multiplication. Now let's talk about arithmetic latency. Before starting about this, let's be clear about two things, that latency and throughput are not the same thing. Latency on the one hand is the time required to perform an operation. Throughput is the number of operations completed per cycle. So where latency on one hand is the time, throughput is the rate. For example, arithmetic operations, they require around 20 cycles and memory operations require around 400 cycles or maybe more to complete one operation. This is latency. On the other hand, arithmetic operations have a throughput of 480 operations per cycle, while the memory operations have a throughput of 32 operations per cycle, which is around 177 gigabytes per second. This is throughput. Now, how to hide latency? Now, one way is multi-threading, but there is one more way that we can hide it by overlapping them with other operations, which means that suppose we have one instruction going on in the system, so while despite of waiting for its latency, we can start another operations or arithmetic instructions side by side. However, this also has its limitations. We cannot start a dependent operation in this time while waiting for the latency of the other operation, first operation, to finish. And however fast it may do, it can never be faster than the peak. Now let's look at an example. Suppose we have three arithmetic instructions which are x equals to x plus a, x equals to a plus b, y equals to a plus c, and z equals to x plus d. Now for execute arithmetic operation 1 and 2, for the first two instructions, they are independent of each other, so we can start them at any time. However, the third one depends upon the execution and completion of the first instruction, so we need to wait for the completion of first instruction to start the third one. Now let's talk about John Little's law. Now, John Little said that the long time average number of customers in any stationary system is equal to the long time average rate of arrival of the customers in the system and the time taken by them to complete a work in that particular system. When we use the same law to get the needed parallelism or maximum parallelism in a GPU, it is latency times throughput. So for example, on a GPU model G80 G200, where the latency is around 24 cycles and the throughput is of around 8 cores per streamlined multiprocessor, the maximum parallelism or needed parallelism is around 192 operations per SM. Now there are different ways to hide arithmetic latency. One is by thread level parallelism, another is instruction level parallelism. In thread level parallelism, suppose we have 4 independent operations like here, that is x equals to x plus a, y equals to y plus a, z equals to z plus a, and w equals to w plus a. Now we can introduce them or inject them in 4 different threads and they can run simultaneously to improve the performance. In instruction level parallelism, instead of injecting in them in 4 different threads, we inject 4 independent operations in one single thread and feed them in pipeline parallelism. That is, suppose while during the execution of the first instruction, that is w equals to w plus a, when it goes from stage 1 to stage 2, and when the stage 1 is empty and waiting, we inject z equals to z plus a, that is the second arithmetic instruction into that to use the time. This is the overlapping we were talking about in the previous slide, and to hide the latency. Now let's talk about a small piece of code over here. Now in the first piece of code, we are executing a equals to a not a into b plus c. This has in a for loop. Over here, the value of unroll is equal to 0, so it will run for n times, and as there is no ILP, so it's basically one thread, one output value per thread. So over here, we need 576 threads to get a peak of 89.6 gigaflops per second, or to achieve 100% utilization. Now in the second case, we have set the value of unroll to 2. That is, we have introduced in instruction level parallelism here. Over here, we are assigning 2 independent arithmetic operations to a single thread, that is a equals to a into b plus c and d equals to d into b plus c. So instead of needing 576 threads to achieve 100% utilization, in the second case we need only 320 threads to achieve the same. Similarly, if we increase the value of ILP to 3, we see that we need only 256 threads to get 100% utilization, and when we set the value to 4, we need only 192 threads to get 100% utilization. So we can say that latency could be hidden in either way. That is, if we set ILP to 1, we need 576 number of threads to achieve 100% utilization, and if we set the occupancy to 12.5%, which is around 1/8 of what we need in thread level parallelism, we achieve similar level of the same level of utilization with instruction level parallelism value equal to 4. So we can say that both thread level parallelism and instruction level parallelism can be used to get to hide the latency on GPU. For example, where we need 25% of occupancy with no ILP to reach the 100% peak. In case of G80, we need only 8% of occupancy if we are running 3 instructions per thread which are running concurrently to each other. Let's take a look at the fallacies over here. People believe that, or this was a common misconception, that increasing occupancy is the only way to improve latency hiding, but it's not. We can also increase ILP and achieve the same. Occupancy is the metric of utilization, which is not the case, but it is the contributing factor. And also, to hide arithmetic latency completely, you need 192 threads, at least 192 threads running on the device of same computing capability, or 384 threads on a device of double computing capability. However, with the coming of G80, GT200, we have seen that similar could be achieved with only 64 threads, and on GF100, the similar could be achieved with 192 threads. Now let's talk about hiding the memory latency. Where arithmetic operations have a latency of near about 18 cycles, a throughput of 32 operations per SM per cycle, and a parallelism of 576 operations per SN, memory operations have a latency which is larger than 800 cycles, a throughput which is larger than 176 gigabytes per second, and the parallelism is higher than 100 kb. That is, if you want to hide memory latency we need at least 100 kb in flight. Now, how can we hide memory latency? Either one way is multi-threading. The second is to use instruction parallelism. That is, we fetch more data per thread. And third is by introducing bit level parallelism. Now, what does it mean, more fetches per thread? This means that suppose if we are fetching 4 bytes of data per thread, then we need 25,000 threads to get 100 kb in flight. And if we are using 100 bytes of data per if we are fetching 100 bytes of data per thread, then we need 1000 threads to achieve the same. Now let's take a look at an example. Here we are copying one float from the memory. Now over here we are just having one output per thread. So to get the peak of we are just copying one float value per thread. So get a peak of 84%. We need 100% occupancy. In the second case, we are seeing here that we are copying, instead of one, we are copying 2 float values per thread. That is, A0 equals to source index and A1 equals to source index plus block dimension into X. We can see here that to achieve the peak of around 84%, instead of needing 100% occupancy, we are achieving the same with only 50%. Now there is one more concept over here. We should not get confused that the threads stall during memory access. The threads do not stall during memory access. They only stall for data dependency. And over here we are accessing the memory, so there is no stalling taking place. Now, if we do the same, like instead of copying 2 float per thread, we are copying 4 float per thread, we can achieve the same 84% peak with 25% occupancy. If we are copying 8 float values per thread, then we achieve the same with around 20% occupancy. If you are copying 8 float 2 values per thread, we are achieving the same for around 12% occupancy. 12 or 16% occupancy. If you're copying 8 float values per float 4 values per thread, we are achieving this 84% peak, or rather 87% peak at around 8% occupancy. And if you are copying 14 float 4 values per thread, we are achieving 84% peak at 4% occupancy, which is phenomenal. So there are 2 ways to hide latency. If we are fixing the number of fetches per thread to 4 bytes, we can achieve 84% at 100% occupancy. And if we have fixed the occupancy level to 4%, we can achieve the 84% peak at around 250 byte fetches per thread. So even here we can say that it's a misnomer that low occupancy always interferes with the ability to hide memory latencies, resulting in performance degradation. In fact, we have seen just right now that we can achieve 84% peak at a mere 4% occupancy. And also that in general more warps are required if the ratio of the number of instructions with no off-chip memory operand to the number of instructions with off-chip memory operand is low. We have seen that 87% memory peak with only 4 warps per SM in a memory intensive kernel. Now let's talk about the third part, that is how to run faster by using fewer threads. Let's suppose we have 32,768 threads in a streamlined multiprocessor. Now there are 2 ways, either we can run more threads or less threads. If we are running more number of registers per thread, then we need lesser number of threads, and vice versa. For example, on GF100, to attain a certain peak, if we are using 40 registers per thread, then we need 100% occupancy, and if we are running 63 registers per thread, we need only 33%. The same can be achieved with only 33% occupancy. Similarly, on GT200, at running 16 registers per thread, we achieve running 16 registers per thread at 100% occupancy, we achieve the peak. But the similar can be achieved by running 128 registers per thread and only 12.5% of occupancy. But is it considered to be better to use more registers per thread as compared to using the shared memory? Now there is a misnomer or a misconception that shared memories could be as fast as the registers. But let's make it clear, registers are the fastest and the largest on-chip memory. Let's look at an example. Suppose we have an instruction, arithmetic instruction, that is A into B plus C. Now over here, the number of inputs is 12 bytes, the output is 4 bytes, and there are 2 flops. So to get 1.3 T-flops per second, we need a bandwidth of 8.1 TB per second. Now let's have a look at the bandwidth available. In the global memory, we have 177 GB per second. That's the maximum bandwidth available. The shared memories are somewhere around 7.6 times faster than the global memory with 1.3 TB per second. And the registers have the bandwidth, maximum bandwidth of 8 TB per second, which is around 6 times faster as compared to the shared memories. So we can see that if we want to execute this instruction, we need registers to reach the peak. So basically, if you're using registers, if you want to run close to the peaks, it is always advisable to use the registers. They are very fast. They are very fast even as compared to the shared memories. And if you're using the more number of registers per thread, you are basically decreasing the occupancy. So one more misconception that increasing occupancy is required for better performance is flawed. If you're using more registers, if there is low occupancy, your performance is going to be even better. Now let's look at a case study, matrix multiplication. We have taken two matrices, which when this matrix multiplication was performed on a GTX 480 GPU, the size which was taken was for the given outline, the given performance on the right side, the was 1024 into 1024. So over here, this is the case where we are just having one output per thread. Over here we are taking there are two memory fetches, that is one fetch per matrix, one memory fetch per input matrix. There is one arithmetic instruction taking place, and there is one memory allocation in the output matrix. So there is only one output per thread. The maximum performance is 242 G-flops, 242 G-flops per second. That is 2 flops per 2 shared memory accesses. And the number of registers which we are using is around 21 per thread. The occupancy is 67%. But since we are using a large number of threads, there is only one block which fits the SM. So we cannot overlap the global memory accesses with arithmetic ones. Now let's increase the number of outputs per thread to 2. So over here in this case, instead of taking one input, fetching one memory access per input matrix, we are fetching two memory accesses per input matrix. We are, in the first case, we are running two arithmetic instructions per thread, and we are assigning values to two matrices, two indices, two output matrix indices. So over here the performance goes up to 341 G-flops per second. That is, the speed has gone up by 1.4 times. We are using somewhere around 28 registers per thread. And so we can see that only by increasing the number of registers by 1.3 times, 2 times more load is being done. That is, we have, instead of having one arithmetic operation, there are twice. The arithmetic operation load has gone up by 2. The output allocation load has gone by 2. The fetching data from the memories has, that load has gone, load has also increased by 2. So overall the total workload has increased by 2. Now we have 2 threads per block. We have 2 thread blocks to fit SM, and since we have fewer threads per block, and so now we can overlap memory accesses with arithmetic operations, which is also one of the reasons for the speeding up, although the occupancy is same. So over here we can also do one thing, that instead of having 2 arithmetic instructions, we can run 2 more arithmetic instructions, which says like here is C sub dot 0 equals to AS matrix 1 tyk into matrix 2 k into tx. Second one says that it's AS ty plus 16k into BS ty, sorry, BS k into tx. There could be third and fourth, where the value of C2 could be AS ty plus 16k and into BS k plus tx plus 16. And so on. So over here, instead, if we are including 2 more arithmetic instructions and 2 more outputs in this particular thread, then the value of the performance will go from 341 to 484 G-flops per second. Sorry, G-flops per second. Now let's take a look at when we want 4 outputs per thread. Here the number of outputs per matrix, the number of inputs or the data memory accesses per matrix has gone up to 4. The number of arithmetic instructions is 4 per thread, and the number of outputs is also 4. So basically we are doing nothing, we are just accessing. If we are accessing T by Tx, we are also accessing plus 8, we are accessing the 16th, and we are accessing the 24th place also, positions also. And similarly we are assigning the output values in the output matrix at position number, at the original position, plus the position ty8, ty16 and ty24. So now we have 4 outputs per thread. The speed is to 427 G-flops per second, which is 1.76 times the speed of the baseline. We are using 41 registers, which is approximately twice the number of registers we were using in the baseline program. The occupancy level is 1.3 times lower, which is around 50%, and we are running 3 thread blocks per streamlined multiprocessor. This this can go on, like if we increase the number of outputs from per thread from 4 to 8, if we then again do it to 12 to 16, the performance can go on and on. But the too far, how can we go too far in this case? Over here the maximum limit is 36. That is, we achieve the maximum, the peak performance as of now in the current scenario on GTX 480 at 36 outputs per thread. Now the number of outputs per if we are having there is direct relationship between the number of outputs per thread and the number of registers we are running to per thread to achieve the desirable result. Over here it is 64. That is the limit. That is the maximum number of registers we can assign per thread to achieve this performance. The number of bytes per flop goes down to less than 1 if we are using 36 outputs per thread. Also, there lies a direct relationship between the number of outputs per thread and the performance, which we have seen even earlier, like in the baseline where the number of G flops was very few as compared to when we increase the output to twice, to 4 times, to 8 times. And over here when we increase the number of outputs per thread to around 36, the G flops also goes up to somewhere around 900. I mean, the performance also increases to around 900 G flops per second, gigaflops per second. Also, the occupancy goes down tremendously as we increase the number of outputs per thread, which we can see that where it was somewhere around 67% for one output per thread, when we are having 36 outputs per thread, it has gone down to somewhere around 30%. That is less than half. So we can say that multi-threading is not the only way to hide latency. If we do more parallel work per thread, we can hide latency even with fewer threads. If we use more registers per thread, we have to access less amount of number of shared memory, which is slower as compared to registers. So this will also enhance the performance of your operations. And these two can only be they can be accomplished only by computing multiple outputs per thread. Thank you.